Now we're going to talk about the volume of gas and the moles of gas and how they are related to one another. This concept, just think about blowing up a balloon. Okay, the more air you put into the balloon expands and gets bigger. So the moles of gas and the volume of gas, they're directly proportional. That's the relationship. This relationship is called Avogadro's law. V, volume, is directly proportional to N, the moles of gas. And we can write another equation to show this relationship, this directly proportional relationship. Okay, it looks kind of like that combined gas law, but this time we've taken out the P, the T, and obviously the R. So this is showing you the direct relationship between the moles of a gas and the volume of that gas. More moles equals higher volume. Alright, so we have another application of this relationship, and it comes from Avogadro. Yes, the same guy. Avogadro's number, 6.02 times 10 to the 23rd. Hey, Avogadro says that 1 mole of a gas at STP has a volume of 22.4 liters. Okay, and that's down here in this statement here. 1 mole of a gas, of any gas, it doesn't matter what type of gas, could be helium, could be hydrogen, could be oxygen, could be nitrogen, it could be carbon dioxide, whatever gas, it doesn't matter the identity, it doesn't matter the chemical formula. 1 mole of that gas is going to occupy 22.4 liters of space. Now, it has to be at this condition called STP. So what is STP? STP stands for standard temperature and pressure. Okay. This is a specific temperature of 0 degrees Celsius. It has to be 0 degrees Celsius. And a specific pressure of 1 atmosphere pressure. Okay, that is the definition of STP. 0 degrees Celsius, also known as 273 Kelvin, and 1 atm of pressure. When a gas, again, doesn't matter the identity of that gas, 1 mole of gas at STP is 22.4 liters. I would definitely write that down, highlight that in my journal. That is a very useful conversion factor when we're dealing with gases at STP. It saves us just a little bit of time, then we avoid that whole ideal gas law thing. Okay, so if I know that the gas is at STP, I automatically know that if there's 1 mole of it, it's 22.4 liters. So if there are 2 moles of it, then there are 44.8 liters. I just multiply it by 2. Okay, so again, it does not matter the identity of the gas. As long as that gas is at STP, we know that the ratio of moles to liters is 1 mole to 22.4 liters. Okay, so here in this diagram here with our dude Avogadro, the balloons of hydrogen, nitrogen, oxygen, it says the balloons all have the same volume. This means they all contain the same number of molecules, and that is correct. Okay, so assuming that these 3 balloons are in the same room, they're going to have the same temperature. So if they have the same volume, then they're going to have the same number of molecules because they have the same amount of moles. So let's apply this. Alright, so we have 3 balloons here, neon, oxygen, and carbon dioxide. Each balloon contains 1 liter of gas. It's at 25 degrees Celsius and 1 atm of pressure. So all 3 of these are probably sitting in the same room, so they have the same temperature, They told me the volume was constant, and that pressure is constant at 1 atm. So they're asking me, are the moles of neon greater than, less than, or equal to the moles of oxygen? And let's explain our reasoning. Well, I could calculate the moles of each one of these gases if I want to. And we would set it up like this. So if I know the volume, the temperature, and the pressure of the neon, which is stated above here, okay, these are the conditions for all the balloons, all the gases in the balloons, then I can use the ideal gas law, right? And I can rearrange that and solve for N. N would be equal to PV over RT. And I would plug in the pressure, the volume, the R, and the T. I would do that for neon. And then I would do that again for oxygen. But since the neon and the oxygen have the same pressure, the same temperature, the same volume, and obviously we use the same R for everything, aren't we going to get the same answer for N? These two gases are at the identical conditions. Same volume, same temperature, same pressure. They got to have the same amount of moles. So the answer is they are equal to one another. And our explanation is because neon and O2 are at identical, or I should say the same, pressure, volume, and temperature. So therefore the moles are going to be the same. All right, let's try another question. Still the same three balloons. Still the same volume, temperature, and pressure. And now I'm just asking you here, is the amount of neon molecules, different word there, greater than, less than, or equal to that of CO2, and explain your reasoning. Well, oh, and they're even asking about CO2 this time. Well, since the volume, the pressure, and the temperature of the neon is the same as that of CO2, I already know that the moles will be the same, as we saw with the previous question. Moles of neon and CO2 will be equal. Okay? And so how do we go from moles to molecules? Isn't 1 mole of a substance equal to 6.02 times 10 to the 23rd molecules? So if these two gases have the same amount of moles, they're going to have the same amount of molecules. The molecules will also be equal to one another because the number of molecules is dependent upon the number of moles. So moles of neon and CO2 will be equal. Therefore, molecules of neon and CO2 will be equal as well. Okay, same 3 balloons, neon, oxygen, and carbon dioxide. Same conditions, round 3, folks. So let's calculate the moles of neon in the balloon. So I know Pivnert, the ideal gas law. I know the pressure. I know the volume. I know the temperature. So we can plug and chug and solve for N. N would be equal to PV over RT. Go ahead and give that a try. Okay, I plug everything into the ideal gas law and solve for N, and I get an answer of 4.5 times 10 to the negative 2 moles, rounding for 2 significant digits. Remember, units, 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 units. We got to be in atmospheres, we got to be in liters, and we got to be in Kelvin. And that's because our R is in liters times atmospheres over moles times Kelvin. So this is one way you could solve the problem. Totally right, you get 100% of your points. Now, there's a little hint here. Neon is at that special condition called STP, standard temperature and pressure. Because standard temperature and pressure is when the temperature is 0 degrees Celsius, which it is. Not 0 degrees Celsius. Hang tight. Big problemo about what I was about to tell you. Hey, this is not STP. I don't know what I'm thinking, guys. STP has to be 0 degrees Celsius. Hint, doesn't help. We are not. No, we are not at STP in this problem. I apologize. So, we're done. We weren't going to use that shortcut then. The answer is 4.5 times 10 to the negative 2 moles. Back up. We're not done. Totally messing up this problem. For whatever reason, I thought we were at 0 degrees Celsius, so when I did my math, my Kelvin is wrong. I apologize. Probably you have a bunch of marks on your paper now. Let's rewind. The temperature is 25 degrees Celsius, so that means it's 298 Kelvin. So I should have 298 Kelvin right down there. Now let's calculate it. Okay, moles is equal to 4.1 times 10 to the negative 2. I apologize. My bad. I had the wrong temperature. The temperature is 25 degrees Celsius, so I had to convert that into Kelvin. So that means this is not STP. You can't use that 1 mole equals 22.4 liters here. Okay, this is the correct answer. Again, I apologize for any confusion. Alrighty, one last problem with these balloons. Now let's calculate the molecules of neon in the balloon. So, well, from the previous problem, I know that the moles of neon is 4.1 times 10 to the negative 2 moles, so we just need to convert that into molecules. To convert into molecules, I know that 6.02 times 10 to the 23rd molecules of neon is equal to 1 mole of neon. Yay, Avogadro's number. And mole day, 1023. Alright, let's multiply. Okay, guys, I get an answer 2.5 times 10 to the 22nd molecules of neon. Again, just using Avogadro's number to convert from moles into molecules.